Hello everyone, welcome to Digital Communication Tutorials. In this video, I am going to take the first numerical on the topic detection and estimation. Please note, this is a numerical on drawing the constellation diagram when you are given a certain set of signals. Let me read out the question first. 4 signals S1 of t, S2 of t, S3 of t and S4 of t are of equal energy capital E and are defined for finite time interval 0 less than or equal to t less than or equal to capital T, and they are defined as S1 of t equals square root of E by capital T into phi 1 of t, S2 of t is equal to square root of E by t into phi 2 of t, S3 of t equals minus of S1 of t, and lastly S4 of t equals minus of S2 of t, where phi 1 of t and phi 2 of t are orthonormal functions defined for the interval 0 less than or equals to small t less than or equal to capital T. Assume the signals are transmitted with equal probability over an additive white Gaussian noise channel. Determine part A of the question, the dimension of the observation space, part B of the question, signal constellation, part C of the question, decision regions, and lastly part D of the question, Euclidean distance between signal points. Right. So, let us now start with the solution part. In the numerical, we are given 4 input signals. Let me just rewrite the signals for convenience at the solution part here. Right. So, from this part we can understand the total number of input signals given here, which is represented by the standard notation capital M equal to 4. Also, it is given in the numerical itself that each of these signals are expressed in terms of 2 basis functions. Therefore, the total number of basis functions is 2. Now, when we come to part A of the numerical, which is to find the dimension of the observation space, we know that it is equivalent to the number of basis functions required to represent the input signals. So, for the part A of the question, the answer is 2. Right. So, that is part A of the question. Now, let us move on to write the part B answer. Part B of the question says, find the signal constellation. First of all, let us identify what is signal constellation. A signal constellation is nothing but a collection of signal points in the n-dimensional observation space. Please note the value n is directly taken from the number of basis functions required. I will now write the definition for signal constellation. For the given numerical, we know that the value of n is equal to 2. Therefore, the dimension of the signal space, as we already have found out in part A of the question, will be equal to 2. Before I start drawing the constellation diagram itself, we must first and foremost note down what are the coordinates of each of the signal vectors in the corresponding observation space. For that, now I will go back and refer to the signals that are given below. Look at S1 of t. S1 of t is equal to square root of E divided by capital T into phi 1 of t. Here phi 1 of t is one of the axes of the constellation diagram. Coming to S2 of t, it is equal to square root of E by t multiplied by phi 2 of t, where phi 2 of t is the second axis. Therefore, all of these 4 signals can now be represented as signal vectors using the coordinates as, I will go for first one, S1, which is the signal vector, is given by square root of E divided by capital T, comma 0. You can come back and see here the constant related to phi 1 of t is taken, but there is no phi 2. So, it is square root of e by t comma 0. In a very similar fashion, S2 will be 0 comma square root of e divided by t. S3 is simply minus of S1. So, it will be minus of square root of e divided by t comma 0. And lastly, S4 is equal to 0 comma minus square root of e divided by t. These are the coordinates of the signal points, and we will now use these coordinates for drawing the signal constellation. Let us start the signal constellation, which is equivalent to the observation space. I will start with the x-axis here, which is our phi 1 axis. Then I have the y-axis, which is the phi 2 axis. Let us now mark the 4 points. S1 is at a distance of square root of e by t comma 0. So, it will be on the x-axis at some point square root of e divided by t comma 0. This is S1. S2 is again at a distance of root e by t, but now is on the y-axis. S3 is at a distance of minus root e by t, but now on the negative x-axis. Lastly, S4 is on the negative y-axis. Right. So, now we have created a constellation diagram. However, the question does not end there, because in part 3 of the question, we are asked to find the decision regions, and in the last part, we are also asked to calculate the Euclidean distance between each of the signal points. So, let us now continue and draw the decision regions for the given constellation diagram. Now, in an important thing, you should note that whenever the signals are transmitted with equal probability and the channel noise is additive white Gaussian, then the decision region, let us say any decision region zk associated with any vector sk, will simply be a set of points that are all closest to sk than any other vector sj. In simple words, a decision region is simply a set of all points closest to a given signal vector. Let me now write that point here. Right. So, we can now identify that since there are 4 message points on the constellation diagram, there will be 4 decision boundaries. Since each of these signals are located on one of the axes, the only possible way of dividing the observation space into 4 equal regions is by dividing each quadrant by drawing a line exactly at an angle of 45 degrees. Right. So, the lines that I just showed here using the green color, they will be the decision boundaries for each of the decision regions. So, let me just mark them out. So, finally, the region between any two decision boundary will simply be called as a decision region. So, I will mark it using a simple curved line like this. Since this is a decision region associated with vector S1, let me call it as decision region Z1. In a very similar fashion, let me draw the decision regions for other 3 signal vectors. Right. So, this will be the constellation diagram for the given signal set. Let us now move on to the last part of the numerical, where we are asked to find the Euclidean distances between the signal points. Now let us come back and check the diagram for signal points. If you consider the signal points S1 and S3, which are simply on the different edges of the same axis, and very similarly S2 and S4, you will find that they are at a distance of 0 to square root of e by t plus 0 to square root of e by t. Therefore, the Euclidean distance between the points S2, S4 and S3, S1 is equal to 2 into square root of e by t. Coming back to the other points, that is the distance between S1, S2, S2, S3, S3, S4 and S4, S1. The distance between these points is simply the square root of the distance from origin to S1 plus origin to S2. That will be the distance between S1 and S2. This is simply by applying the Pythagorean theorem. So, I will now write the distance between those points as, please note this is by using Pythagoras theorem. Right. So, with that we have completed this numerical. If you like this video, kindly like and share this video and subscribe to my channel for more information on digital communication. Thank you for watching. Have a good day.